Welcome all. Welcome to today's online class. Today we are going to discuss the second type of molecular spectroscopy which find immense application in organic chemistry. That is IR, infrared or vibrational spectroscopy. The basic theory of this spectroscopy might have been dealt in 5th semester. However, before we go into the application part, we will make a quick recap of the basic concepts. Why this is called vibrational spectroscopy? Because IR spectroscopy involved vibrational transition of molecules. And it is called IR spectroscopy because for this vibrational transition of molecules, we require infrared radiation. Compared to UV visible spectroscopy, which we discussed in the previous sessions, this is more useful for structural elucidation. We are mainly concerned with knowing about what is called group frequencies, the values, the IR data, and then applying it. How we can interpret a given IR spectrum, how we can reduce the structure of an unknown compound if you are given the IR data, etc. Before that, let us make a quick recollection of the basic principles. First of all, origin. This spectroscopy originates from the fact that the bonds in a molecule are undergoing vibrations. It's like a spring. Actually, molecular spectroscopy is fundamentally a quantum mechanical problem. So for each spectroscopy, we will write the what is called Schrödinger wave equation and put the energy parameters and solve the equation to get the quantized energy levels for various spectroscopy. That all comes in your 5th semester. And here, qualitatively speaking, see this bond, for example HCl, bond is like a spring. It is vibrating. If there is one bond, it can have about the mean position or equilibrium position. It can either undergo stretching, extension, increase in bond length, and then come back to the original bond length and then decrease. So extension and contraction, this continues. This is stretching vibration. Change in bond length takes place. This is called stretching vibration. Say that HCl is a polar molecule. So this vibration will create change in dipole moment. So remember, the condition, necessary and sufficient condition for a molecule to be IR active or to give IR spectrum is that vibration should accompany with change in dipole moment. That's called selection rule, Gross selection rule. So if we put molecules which are IR active, we can put HCl, similarly H2O, NH3, etc. What about molecule like H2, N2, etc., which are homonuclear diatomic molecule? These are non-polar, right? Bond is not polar, non-polar. Even if it vibrates, there is not going to be any change in dipole moment. So these are not IR active, but these are IR active molecules. So that's the origin of IR spectroscopy. So due to this vibrational motion, molecule will have various vibrational energy levels, quantized vibrational energy levels. Normally molecule will be in the ground state. If we are supplying IR radiation, the molecule can get excited to higher vibrational levels by absorbing IR frequency. That gives rise to IR spectrum of a molecule. Now, during vibrational transition, you might have learned that a molecule moves from lower vibration level to higher vibration level, right? And that is governed by selection rules. Like what is the change in quantum number possible? Vibrations are of two types, you might have learned that. That is vibration which follow Hooke's law, that's called harmonic oscillations, and it can be mostly anharmonic also. In the two cases, there is slight change in the selection rules. Okay, that whole part we are not concerned with here. Anyway, this is the basic principle of IR spectroscopy. So it involves transition of molecules from lower vibration level to higher vibration level by absorption of electromagnetic radiation from IR range, because the vibration energy gap corresponds to the energy of IR radiation, and that is governed by quantum mechanical selection rules. Now coming to the IR range used for the study. See, IR, you know, is the part of electromagnetic radiation having larger wavelength compared to visible, right? IR, infrared. It can be split into three parts. IR can be split into three parts. The part which is close to red is called near IR. IR which is close to red. And this is called far IR. And this is called middle IR. Okay? So there are three parts. Now, for convenience, the energy of IR radiation is represented using wave number in centimeter inverse. Whereas in UV visible spectroscopy, we were using wavelength in nanometer. Here it is wave number we use in centimeter inverse. Far IR ranges from, the value is from 50 to 667 centimeter inverse. Okay. Then middle IR, that is most important, 667 or 700 roughly to 4000 centimeter inverse. And near IR is from 4000 centimeter inverse to 12,500 centimeter inverse. We are interested, or spectroscopists are interested in this middle IR, or this is the range of IR used for this spectroscopic purpose. Which one? 667 or roughly 700 to 4000 centimeter inverse. Keep that in mind. Now, before we go into the main part of the discussion, that is the group frequency, one more point to be discussed is about the types of IR vibrations. Actually, it is very interesting to see how the molecules are vibrating. We can classify vibrations into many types. See, vibrations are mainly of two types. This is again a portion which came in 5th semester. Molecular vibrations can be of two types. What is that? If you remember, one is called stretching vibration. See that you are supposed to revise your 5th semester theory of IR for understanding this discussion. Stretching, and the other is bending vibration. Vibrations are two types, stretching and bending. What is the difference? Let us take, for example, carbon dioxide molecule. Okay, CO2, you know, it's linear molecule. Okay, CO2. Or more better, let us take another example. See, any organic molecule contain, many of the organic molecule will have this grouping, that is methylene group, right? Ch2 part will be there in most of the organic molecules. So this is methylene group. There are two CH bonds. Okay, it is something like water. You can understand. It's a V shape like this. Now, stretching means the bond length changes. That is stretching vibration. If there is change in bond length, that vibration is called stretching vibration. Now, this is again of two types. Stretching vibration is again of two types. One is symmetric stretching. The other is asymmetric stretching. Bending is of again two types. In plane bending, in plane, and the other is called out of plane, right? I will quickly show you all these things. Suppose we have these two bonds. See, this, suppose these are the two CH bonds, okay? Methylene, carbon, hydrogen, here also hydrogen. What is stretching vibration? The bond length changes. It can happen in two ways. That is, either the two bonds can simultaneously elongate, increase the bond length and come to the mean position, and then decrease, contract like this. See, this is the bond length, this increasing, come back and decreasing like this. This kinds of vibration is called symmetric stretching. Another is asymmetric stretching, that is these two bonds, the CH bonds, okay, the CH bonds, one bond is elongating, meanwhile this is contracting, and then this is elongating, this is contracting. That way also it can happen. A little more difficult type of vibration which require more energy. Remember, asymmetric stretching require more energy or higher frequency IR is used for this transition. So there is asymmetric stretching. The two bonds are stretching in opposite direction. See, it is something like our common exercise which we do. Like, see, when you do this kind of rotation of hands, you can do it in the same direction. Okay, or one in this way and one this way. It's a little difficult, right? That is kind of asymmetric kind of rotation. So like that, there is symmetric stretching and asymmetric stretching. And coming to bending, what is bending? It is a vibration in which bond angle changes, whereas in stretching it is bond length changes. Here it is bond angle changes. See, for any vibration to be IR active, I repeat, what is a condition, essential condition or the selection rule? There should be change in dipole moment. See, if these two bonds are vibrating, changing in the bond length, you know, dipole moment is depends on the bond length. When it changes, of course, the dipole moment will vary. Similarly, when bond angle changes, see, this bending can be two types, in plane and out of plane. What is that? See, you keep these two CH bonds in a particular plane and then you are changing the bond angle. In this in plane is again of two types actually. Again of two types. This is also again of two types. What are the two types? Let's see. Okay, see, look here. This is a bond angle, whatever it is. If it is tetrahedral angle, you know it is 109 degree 28 minutes. Now bond angle is now decreasing. Come back to mean position, increasing like this. This kind of bending vibration. This is an in plane because this bending takes place within the plane in which these two bonds remain. Correct? So this is called scissoring. In plane is of two types. One is called scissoring, movement of a scissors. Another is that in the same plane, both the bonds are moving in the same direction like this. This kind of bending is also possible. One is this, the other is like this, it can move. In both cases, when bond angle changes also, you know, the vector sum will change, dipole moment will change of the bonds. Resultant dipole moment will definitely vary. And finally, out of plane. See, the bonds can move out of plane with change in bond angle. That can also take place in two ways. One, this is the plane. Both the bonds are coming out of the plane, above the plane, go below the plane like this. This is called wagging, right? And finally, the two bonds go out of the plane in opposite direction, like one bond goes up, the other goes like this, out of plane, going like this. This is called twisting. See, altogether, it's very interesting. You can call it molecular dance. The bonds are stretching, bending in different ways. All these give rise to different types of vibrational energy levels for the same molecule. And you get so many kinds of vibrational transitions possible in the molecule, and that give rise to a large number of IR peaks. Okay, now we go on to the crux of the discussion. That is what you are mostly concerned in 6th semester, how you can interpret IR data. So listen, what is called group frequencies. Concept of group frequency. See, in a molecule, suppose you have a big molecule like phenol, right? Benzene is there, OH is there. This OH bond is vibrating. It is believed that this vibration of this OH group is not influenced by the rest of the molecule. Means each group present in the molecule have got individual individual independent vibrations. So scientists studied on this. They took a large number of related molecules. For example, you take methanol, ethanol, hexenonol, phenol, etc. All are alcohols, OH group is there, and they took the IR spectrum of all these compounds and they noted the IR frequency absorbed from the spectrum, and they could formulate some basic data. That is what is called group frequency. So group frequencies are the specific standard basic IR absorption frequency for various functionalities. I have given here the significant impression of the data, not the whole. If you Google out, you can check IR data, IR frequency data. You get a very detailed table indicating various types of functionalities. But for our purpose, this is more than enough. And then you can develop to higher levels. And I will quickly go through these values to make you familiar with these values. One point to be noted is, in the theoretical discussion, the IR frequency absorbed by a molecule for the transition is given by the equation 1 by 2 pi c root of k by mu. Okay, so the IR frequency absorbed depends on k. What is k? Force constant, right? Force constant, and that comes in the theoretical discussion. Mu is called reduced mass, which is m1 m2 by m1 plus m2. You go back to your fifth sum portion for detailed understanding of this. Anyway, let's see the values. We are going from a higher to lower value. I have told you already that we are concerned with the middle IR range, ranging from 667 to 4000 centimeter inverse. Okay, so we are coming from higher to lower value. Look, the first two groups having highest IR frequency values, OH and NH. Where you find this? OH is there in alcohol, in carboxylic acid, etc. NH in amines, amide, etc. These are having generally value 3400. Okay, so this is the highest IR frequency value possible for a functional group. That's for alcohol and amines. An interesting point, you should understand why these values and what are the changes, exceptional cases and all. This value many times decreases to 3200. Frequency decreases when it is hydrogen bonded. You know that alcohols and amines are very much hydrogen bonded, you know. There will be intermolecular hydrogen bonding like this. Okay. So mostly there will be intermolecular hydrogen bonding. So due to hydrogen bonding, this bond will become weak, you know. When a new bond appears, it will be at the cost of this bond. This bond will become weak. When bond weakens, that means in the equation, nu is equal to 1 by 2 pi c root of nu or nu bar k by mu. So when the bond weakens means force constant decreases, then frequency will decrease. That's why value decreases. It can even go further down, even 3100, etc. Actually, there is a scope of research here. You can study the extent of hydrogen bonding by noting the decrease, how far IR frequency has decreased. Another thing is that whenever there is hydrogen bonding, the IR peak will be very broad, not sharp. The next one, CH. CH bonds will be there in most of the organic molecules. If it is aliphatic, the value will be less than 3000, slightly lower. That's how you remember this. It is roughly 3000, and aliphatic, if it is aliphatic, like 2850, 2900, like that. If it is aromatic, that means basically this is sp3 carbon, this is sp2 carbon. Even in alkenes also, the value will be a little above 3000 because the bond becomes strong, right? If this is sp2 carbon, you know, it is more electronegative and this bond becomes stronger, and actually this bond is stronger and it is a little higher, 3050, like that. Then this very notable one, that is the CH bond of aldehyde group has a very peculiar peaks, IR peaks. 2 peaks you get, that is 2800 and 2700. This may get overlapped with this peak, that is aliphatic CH stretching may get masked, and this you may not see actually. There is another difficulty in interpreting IR spectrum, that many peaks may get overlapped. You may see only 1 peak instead of 2, so you may have to be very keen in observing, in interpreting an IR spectrum. We will discuss IR spectrum examples in the coming class. Then for C triple bond and C triple bond C, this mostly comes to 2200. We are coming down the values. And then remember, this CO carbonyl group is the most important peak in IR. Any IR specialist technician will, IR spectroscopist will first look into whether the molecule has a CO peak, because it is most intense peak. Most intense, because this is highly polar, okay, and so many factors are there. For carbonyl group, see now carbonyl is very much present in many compounds like aldehyde, ketone, carboxylic acid, and all the derivatives. Its value basically is 1715 centimeter inverse. It can increase to this or decrease to this when CO is, that is the case of acid derivatives, right? If it is connected to X, means acid halide or ester OR, this will have minus I effect, you know. Due to minus I effect, this bond will become strong. When there is an electron withdrawing group here, this bond will become stronger. Then frequency will increase to 1740 or even higher. Here, in the case of amide, it's interesting. There is resonance possible due to the lone pair, and you know there is conjugation. What happens? This CO group get partial, the double bond character decreases, or it get partial single bond character, and this bond become weak. So frequency goes down below even 1700. Then carbon-carbon double bond present in aromatic system, in alkenes, etc., characterized by these peaks. 2 peaks you get, 1600 and 1475 centimeter inverse. Then Ch2 bending. See, organic compounds will have many Ch2 methylene groups, and I have just shown that Ch2, and that can have bending vibrations in plane and out of plane, and there are 2 peaks. Then NO2 nitro group, you know, nitro group is this, correct? And double bond or single bond. So this can have symmetric and asymmetric stretching and give rise to 2 peaks, 1550, 1350. Remember, these peaks are all close by, so one may get masked by the other, get overlap. You may not see all these peaks, sometimes overview all this. Finally, C single bond or C single bond N, very weak bond, single bonds, you know, and the value is 1100. Okay, so these are some very important functional groups and their corresponding characteristic IR group frequency. Have a clear idea about these values, and this become more clear when we go to some important molecules and their IR spectrum in the next class. Till then, bye.